To another screencast. I'll be discussing Punnett squares here, and so by the end of this, hopefully you are able to describe and explain the Punnett square. So the components of a Punnett square, the purpose of using a Punnett square, what the Punnett square can tell you and what it does not tell you, and then B here, just be able to describe and explain how to use the rules of probability so that you never ever have to use a Punnett square in public again, right? You don't want to be that kid using a Punnett square when there's no real need to. Okay, so the Punnett square allows you to predict combinations of gametes in the next generation. So this is what a Punnett square can do for you. It helps you to predict the combinations of gametes, right? That is the result of fertilization. So you can predict the results of fertilization. So the components of a Punnett square, so let's do a monohybrid crossing, and this is a monohybrid cross because we're looking at one character here, and that's flower color. So the character I'm looking at is flower color. Flower color. And each of these flowers here is purple, and they are both heterozygous. So this is the hybrid part, is that we have two heterozygous parents here. So now on the Punnett square, I want to know then what kind of, if I cross these two, that is mate them together, what kind of possible gamete combinations can I get? Right? What are the results of fertilization going to be? What could they be? Right? So if you look at this, you can say that this heterozygote parent right here can produce big P gametes, so half of the gametes will be big P and the other half of the gametes will be little p, because of course these are on homologous chromosomes that then separate in meiosis to produce the gametes. This parent here has a 50% probability of producing big P gametes, and 50% of those gametes will be little p. So that's what goes here on the outside of the Punnett squares, are the possible gamete genotypes. So these are the possible gamete genotypes there for one parent, right? So these are the sperm, and then these right here are the possible gamete genotypes of the other parent, right? The ova, right? The egg here. So then everything in the box is a potential result of fertilization. So these show you all of the possible potential results of all possible matings, or all possible fertilization combinations. It's rather wordy, but this is what these boxes are showing you. So you'll then predict what are all the possible gamete combinations, right? So that, again, another way of saying this is that the boxes are all of the possible gamete combinations. That is results of fertilization. Okay? So when you do this, right, you can say, here's big P, etc. Right? So you then know that you have a 3/4 possibility of getting an offspring. So 3 out of the 4 offspring possible are going to be purple, right? And 1 out of 4 will be white down here. And this is where you get this 3-to-1 ratio. So 3 out of 4 and 1 out of 4. So a 3-to-1 ratio, right? So this is 75%, right? 3/4 is 0.75, right? And 1/4, right? 25%, 0.25, right? So 75%. So this is a visual representation of what's going on there. Okay, so there's the monohybrid cross. You can also apply this to a dihybrid cross, and again, the key with the dihybrid cross here is that this works if the two characters are on different chromosomes. This is a key, right? If they're on different chromosomes. So you have to assume independent assortment here, right? That is, how the Y's behave is independent of how the R's behave, right? So this is a dihybrid cross, right? 2 characters, so the di, right, is 2 characters. And so in this case we're dealing with seed color and seed shape. So these are the 2 characters, where the Y is for the color and then the R's are for the shape. Now these are hybrid because you are hybrid at both loci. So at the Y locus you are heterozygous, and at the R locus you're heterozygous, and this is heterozygous, and then heterozygous over here at this R locus as well. So what the question is, what possible gametes can this parent make? Well, again, here these are all the possible gametes, all possible genotypes of the gametes, right, for one parent, and then you list all the possible genotypes of the from the other parent here, right? So that's what goes on the outside of them. And then the boxes here, right, all the boxes here represent, again, all the possible combinations, right? All possible gamete combinations due to fertilization, right? So not saying that that these 2 parents are going to mate and produce 16 offspring every single time. This is just telling you the probabilities, right? The possibilities here, the percentages, right? So what's the probability that you get a yellow seed from this? Well, if you just visually look at this, right, you know, yellow looks like about 3/4 of them are yellow and 1/4 of them. But you're dealing with 2 at the same time here, right? So what's the probability that you get a yellow round, right? Yellow round. Well, that's a yellow round. So 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 out of how many boxes? 16. Well, here it is, right down here. 9 out of 16 are yellow round. Right? 3 out of 16 are green round. 3 out of 16 are yellow wrinkled, and 1 out of 16 are green wrinkled. So you get your 9 to 3 to 3 to 1 ratio here phenotypically, right? Now, in case you're wondering about genotypes here, the genotype ratio is a little off the hook, right? I mean, you can go through here and count these up, right? But it looks something like 1 to 2 to 1 to 2 to 1 to 4 to 1 to 2 to 1 to 4, no, to 1 again, something like that. Who cares, right? It doesn't matter. You're never going to be asked about that. But again, you're assuming independent assortment here. So what's going to happen? Let's go back up here again and just look at these possible genotypes of the gametes, right? So this parent right here can make you can get the big Y with the big R. You can get the big Y with the little r. You could then get the little y with the big R, and you could get the little y with the little r. So these are all the possible gamete genotypes here. And what's the probability of getting this? This is 1 out of 4. Right? This parent is going to make all of these in equal proportions. This parent here is going to make all of these in equal proportions, right? So the likelihood of getting any of these combinations here, right, getting this one fertilizing this one is as likely as this one fertilizing this one over here, etc. Right? So you can use the Punnett square there if you want. However, the rules of probability can, and I would argue, should be used to solve here genetics problems, right? And again, the rules of probability, we're talking about the rule of multiplication and the rule of addition, right? Multiplication and addition. And this is the little tutorial sheet that I had you fill out and practice doing here. So the probabilities of 2 independent events, right? This person flipping a head is independent of this person over here flipping a head. So what's the probability that this person flips a head? Well, that's 1 out of 2, or 0.5. Probability that this person over here flips a head is also 1 out of 2, or 0.5. This person flipping over here is independent of this person flipping. Just because this person flipped a head doesn't mean this person is any more or less likely to flip a head, right? So what's the probability of both of them flipping heads at the exact same time? Well, that is the rule of multiplication here. So the probability of this person flipping heads is 0.5, this one 0.5. You multiply those together, 0.5 times 0.5, and you get 0.25, or 1/2 times 1/2 is 1/4, right? And so one out of those four boxes there is head, sorry. Okay? Same logic over here. What's the probability of getting a heterozygote this way, right? Where this one flips a head and this one flips a tail. Well, probability here is 0.5 and 0.5, so the probability of getting tail head is 1/4. What's the probability of getting head tail? Well, that's also 1/4. So what's the probability of getting a head and a tail? Well, you take both of those probabilities and you add them together, right? Because you could get a head and a tail this way, or you could get it this way. So rule of addition says if you can get a result in more than one way, so if it can happen this way or this way, use rule of addition. Rule of multiplication, if you want two independent events happening at the same time, you want this and this happening, you multiply each individual probability together. Okay, so applying that to the Punnett square, right? It's going to work. It's going to work the same way, right? We just saw that here. So what's the probability that this parent? What's the probability that this heterozygous parent produces a big P? Right? Well, that's 0.5, right? Half of that. And what's the probability that it produces a little p gamete? 0.5. So same thing over here with this individual, right? Is 0.5 and 0.5 to get a big p gamete or a little p gamete. So what's the probability that when I cross these, I get little p, little p? Well, I know that this little p had to come from one of the parents, right? So the probability of getting this is 0.5. What's the probability of getting this? Well, it had to come from this parent. Well, the probability of this parent producing a little p is also 0.5. So I want that and this. So and means I multiply, and that is 0.25, or 1/4, right? 0.25, 1/4, one out of those four boxes up here, right? So this is the math, and it works its way, right? Works its way out. Works for the dihybrid cross very, very similarly as well, right? So given these two parents right here, let's do it over here a second. So given these two parents, right, heterozygous at both loci, right? What is and I cross them, what's the probability that I get big Y, big R, little r? Well, since this is independent assortment, I can treat these as two little separate crosses, right? Because how the Y's behave is independent of how the R's behave. So what's the probability from this cross that I get this? Well, the probability that this parent gives a big Y is 0.5 and this parent gives a big Y is 0.5. So 0.5 times 0.5 is 0.25. Well, what's the probability that I get big R, little r? Well, I can get big R, little r in more than one way. Right? I get parent 1 giving the big R, parent 2 giving the big R, that's 0.25. Or I get parent 1 giving the little r, right, and the parent 2 giving that, so that's 0.25. So I can get that in more than one way, or I add those together as 0.5. So what's the probability that I then get this and this at the same time? That is, I get this and this. Well, I multiply those two things together, right? So 1/4 times 1 out of 2, right, is 1 out of 8, right? So 1 out of 8, so this is 2 out of 16. So 2 out of these 16 boxes up here should have this genotype in it. And let's go just hunt for it real quick and see if we can find it. It's going to be this one right here. Here's one of them, and then here's the other one right here, and those are your 2 out of 16 boxes, right? So you don't need to do this, right? This is pretty handy because now what if I want trihybrid, right? If I want trihybrid, how big is this Punnett square? Well, if the monohybrid is a 2x2 and the dihybrid is a 4x4, then the trihybrid is going to be an 8x8, right? So that's going to be 64 boxes that you're going to have to be filling in, right? What if it was a tetrahybrid cross here? Well, that's going to be what? 8x8? No, it's going to be 16x16, right? So 256 boxes here. No way, you can't do this, you can't do that. But what if I was to give you this and say, just to see if you're following this, right? What's the probability of, from this cross of getting this as a as an offspring, right? And from this, what's the probability of getting this guy here, E, and then little g, right? So use the rules of probability here and see if you can figure that out, and then come to class. That's something to kind of work on there. Right? Thanks for listening. So hopefully here now you're able to understand the components of a Punnett square, what the purpose is, right? What it tells you, what it doesn't tell you, and then how to use here the rules of probability so that you should not ever have to use a Punnett square. Right? That is never ever again. Okay? Thanks for listening. Bring your questions to class.